Welcome to our second module in our Introduction to Doka for DPUs DLI course, titled Introducing Bluefield DPUs. In this module, we'll take a deeper dive into the family of Bluefield DPUs and their acceleration capabilities. Doka exposes these acceleration capabilities often in a few different ways, depending on the persona that needs to use it. So let's get started.
This module has two main sections. We'll open with a broad overview of the Bluefield product family and a bit about the Bluefield system software. Then, we'll transition into talking more in detail about Bluefield DPU's current acceleration capabilities. It's important that for understanding Doka as an enablement platform, to understand the underlying hardware and its capabilities. So first, what are all of these new terms emerging in the industry, and how do they relate to Bluefield and what it actually is? Depending on the context, all of these terms describe what Bluefield is: system on a chip, SmartNIC, functional offload processor. Yes, Bluefield DPUs fit the description of all these terms. In our vernacular, we find that DPU best describes Bluefield. SmartNIC is also a popular term, but it doesn't really capture the whole picture and the whole set of Bluefield capabilities that render the need for a different class of network cards. Today, we're shipping Bluefield 2 DPUs with Bluefield 3 coming soon and Bluefield 4 on the horizon. Remember that Doka is the enablement platform for Bluefield DPUs. So said differently, the Bluefield DPUs are the Doka hardware platform. Some quick highlights of Bluefield 2's capabilities include up to 200 gigabit per second for both Ethernet and InfiniBand powered by the award-winning ConnectX-6 family of host adapters. But in addition, a whole suite of additional accelerators and processing capabilities, including 8 ARM cores with up to 8, 16, or 32 gigabytes of DRAM, a regular expression engine, a public key acceleration engine, compression and decompression engines for storage, and some models equipped with a GPU for AI and ML workloads, all connected by an integrated PCIe 16x Gen 4 switch to act in either endpoint mode or as a root complex. The end result is a massively flexible platform for offloading and accelerating data center infrastructure functions, again, all enabled by Doka. So Bluefield is really the name of the product family, but it's important to note that some DPUs may have slightly different names depending on what they offer. There are different form factors of Bluefield DPUs. Some Bluefields have local storage memory on top of them. Others designed to act as a PCI root complex, so you can build your entire system around the ARM cores and the DPU, and not as a secondary set of cores. And as we just discussed, some Bluefield DPUs include a GPU to provide a robust compute offload feature set. Bluefield DPUs have some models with a built-in BMC. Since the DPU is in many ways its own server, a means of bootstrapping and provisioning the DPU without any dependencies on the host machine are important for maintaining a fully isolated and secure enclave separate from the host. The Bluefield family of DPUs are on a trajectory to keep pace with the speed of data center networking. Bluefield 2 accelerates up to 200 gigabits per second networking, with Bluefield 3 positioned to handle 400 gigabits per second, and upwards to Bluefield 4 as the generation to accelerate and power the next generation data centers utilizing 800 gigabit per second data rates. It's important to note that Doka, being the enablement and development platform for DPUs, will protect your development investments and software architectures as new generations of more powerful DPUs are developed. Bluefield 3 DPUs are the next in line and third generation of the Bluefield product line. Bluefield 3 will offer speeds of up to 400 gigabits per second and provide more bandwidth, more compute, more programmability, more acceleration compared to previous generations to improve data center performance, efficiency, scalability, and security. Fully utilized, a single BlueField 3 DPU can be equivalent of up to 300 x86 CPU cores, compared to BlueField 2 was roughly 125 CPU cores. As a quick comparison between the BlueField 2 and BlueField 3 generations, we can see how much more powerful the upcoming BlueField 3 will be. BlueField 3 is faster across every feature and important metric, and will even add additional acceleration capabilities such as MACsec acceleration for line rate layer 2 link encryption. Now let's talk a little bit about BlueField software and provide a little overview of how it's put together and how it works. We're going to see a lot of stack diagrams through this course, and what we're illustrating here is a bit more simplified and generic view of the software components of a BlueField system. Because BlueField acceleration features are available and exposed to both the host and ARM cores, we see bits of software for BlueField in both places. Naturally, a BlueField card is installed in a supported server running a supported operating system. Support exists for Red Hat Enterprise Linux and CentOS, Ubuntu and Debian, and Windows on the host. The drivers on the host depend on the host OS, and then applications and services that leverage the BlueField leverage those drivers. Doka would describe all of those boxes on the host except for the host OS. That's the drivers, the runtime libraries, and tools and management utilities are software packages that in its broadest sense earn the label Doka and are part of the total enablement platform. It's useful to think about BlueField as a server. It runs daemons and can be managed in many of the same ways as a physical server, especially with models that contain a BMC. However, models without a BMC utilize a management tool called Arshim that uses PCI or USB interfaces to provide a means for imaging and bring up and other low-level system configurations. We'll spend some more time with this in an upcoming module. There are two major modes of operation for BlueField DPUs. There are a few others, but conceptually, these are the two most important modes of operation to understand packet flow through a BlueField. Separated host mode is also known as legacy mode or symmetric mode. In this mode, both the host and the embedded ARM CPU share control of the embedded switch and physical port functions. Each has its own MAC address and is able to send and receive Ethernet and RDMA over Converged Ethernet or RoCE traffic. Also, there is no dependency between the two functions. They can operate simultaneously or separately. The host can communicate with the DPU interfaces as two separate hosts, each with its own MAC and IP addresses, configured as standard interfaces. In embedded mode, the network interface resources and functionality are owned and controlled entirely by the DPU and software stack. A network function is still exposed to the host, but it has limited privileges. In particular, the driver on the host side can only be loaded after the driver on the embedded side is loaded. With ownership of the network interface and embedded switch functions, it means that traffic to and from the host interface always lands and goes through the DPU in both directions. In embedded mode, there are two ways to pass traffic to the host interfaces. Either using representers to forward traffic to the host, so every packet to and from the host will also be handled by the network interface on the embedded ARM side, or to push rules to the embedded switch, which accelerates and offloads the flow for line rate performance. We just discussed briefly the two main modes of operation, separated host and embedded mode. There is also an additional mode called restricted mode, which is in many ways the same as embedded mode, except that it provides limited access from the host to be able to reach, change, or update the BlueField in order to enforce a truly isolated administrative boundary between the host and the DPU. Without running it in restricted mode, it's possible to access the DPU from the host and make configuration changes that may allow for evasion of security policies enforced on the DPU, or tampering with configuration and services that could affect infrastructure services. Now let's dig a little deeper into the specific types and uses of accelerations and offloads that Bluefield and Doka can offer. It's important to note that this isn't an exhaustive list, and in many ways, these acceleration features and use cases are driven by software. As the Doka and Bluefield ecosystem grows, expect that new and novel ways to use the hardware accelerators and software can create new acceleration features to expose and enable with Doka. Encryption is an important aspect of security architectures. Whether it's storage or data transmission, the computational work required to perform encryption and decryption functions can quickly consume most of the CPU cycles of general-purpose CPUs at data center throughput rates. Bluefield DPUs provide dedicated hardware acceleration engines to perform the symmetric encryption and decryption that's used for network-based transit security. Notice that by moving the encryption function down to the DPU, the host no longer needs its own general-purpose CPU to perform those operations, and can let the DPU handle security encryption as part of its own network function and alleviate the responsibility on the application. Similarly, with encryption and decryption accelerators, Bluefield DPUs can accelerate and offload the hard work of encryption and decryption for transport layer security connections. Compared to IPsec, TLS provides a secure socket to an application instead of a dedicated secure tunnel between two IP endpoints. TLS depends on several public key operations during its handshake and leverages other built-in acceleration engines to offload those functions and allow for higher connection per second rates. As we touched on with TLS, Bluefield contains a public key operation acceleration engine to offload OpenSSL public key signature operations. This includes RSA 2048 and 4096-bit signature and verify operations, Diffie-Hellman, DSA, and ECDSA signature algorithms. It also includes a true random number generator to help ensure random numbers are truly random and not generated algorithmically. This acceleration engine can help reduce overhead for use cases such as a web HTTPS server that leverage TLS to help reduce the overhead of the TLS connection setup and handshaking where these sign and verify operations occur. Regular expressions have a wide range of use cases. For networking security software like next-gen firewalls or intrusion detection, the major bottleneck and most of the processing time is spent pattern matching for application layer threats beyond the static packet headers. Most of the size in bytes of network traffic is data payload, and that varies in size or length. Threats can exist anywhere in the payload of a packet, and it becomes difficult to efficiently search through each packet's payload for a variety of threats at high data rates. Bluefield provides a regular expression engine to accelerate and offload the processing of pattern matching for network packet payloads. This significantly reduces CPU overhead for accelerating applications and use cases such as intrusion prevention, stateful load balancers, DDoS protection, and web application firewalls. Now let's talk about a different type of acceleration. This one's much more abstract and a little bit more difficult to see and find opportunities to leverage, but the ARM cores that power the DPU are also their own accelerators with respect to the general-purpose CPUs on the host. The goal isn't to simply port entire x86 applications to run on ARM on the DPU, although sometimes that is the case, such as an IPsec control plane, but the point is to move relevant and manageable portions of the application that relate to things like infrastructure, security, and storage down to the DPU ARM cores. A Kubernetes CNI is a great example of this. Classically, an OVN-based Kubernetes CNI needed to run entirely alongside the pods and container runtime, costing CPU cycles for moving packets around the overlay. With DPUs, it becomes possible to move the OVN and OVS components and the data path processing down onto the DPU, leaving the host more power for orchestrating and powering the containerized applications. Another type of network acceleration and offload function is the VirtIO net acceleration. This is another great example of the DPU ARM cores as accelerators that we discussed in the previous slide. VirtIO net devices can be provided and emulated by the Bluefield ARM cores, and then used on the host without the performance penalty to the CPU of the hardware emulation functions, which are a function of software and general purpose processing. Turning towards storage, another key pillar of Bluefield DPU use cases, we find even more acceleration capabilities. Bluefield provides options to reduce CPU usage by handling the compression and decompression, encryption and decryption of data. We also have support for T10 diff for data encryption both at rest and while in flight. Some storage partners support end-to-end storage integrity from the storage controller to the hosts. With InfiniBand, CPU and memory resources for the storage and compute clusters are freed up with T10 diff offloading. The read throughput with diff enabled is the same as that of diff disabled. Hence, diff offloading can provide data integrity protection without sacrificing performance. Bluefield also provides storage emulation functions. Both NVMe and VirtIO block snap emulation are available. NVMe Snap is storage-defined network accelerated processing, presents network storage as a local NVMe SSD by emulating an NVMe drive on the PCIe bus. The host OS or hypervisor then makes use of its standard NVMe driver, unaware that the communication is terminated not by a physical drive, but by the emulation on Bluefield ARM cores. Any logic may be applied to the data via the NVMe Snap framework and transmitted over the network on either Ethernet or InfiniBand protocols to remote storage targets. Similarly, VirtIO Block Snap presents a VirtIO block device to the host OS or hypervisor. The host OS or hypervisor can then use the device without spending CPU cycles providing that emulation. That emulation is accelerated and offloaded by the Bluefield ARM cores. That wraps up our module covering an overview of the Bluefield DPUs and their capabilities. Looking back, we discussed the Bluefield family of DPUs and what sets them apart from other accelerators. We discussed the trajectory of upcoming Bluefield DPUs and briefly looked at the next DPU, Bluefield 3. Then, we covered some more of the acceleration capabilities that Bluefield offers and a bit about how they're implemented. Thanks again, and we'll see you in the next module.